So direct product groups, the basic idea is, in any kind of mathematical theory, once you've got a few examples, and we mentioned a few examples last week, you want to start building more complicated examples from the ones you've already got. And there are two basic constructions in algebra that give you new objects from ones that you've already got. One way, which we're going to move on to shortly, is to take sub-objects. So when you've got sets, you can look at subsets. We're going to have groups, and we're going to look at subgroups, which are groups sitting inside bigger groups. The other method of constructing new objects is to take products. So if you've got two sets, you can take the Cartesian product to get a new set. And in fact, if you've got two groups, you can take a product called the direct product to get a new group. So I just want to discuss that briefly now and do a little example. And we'll be using this in and among from now on. But it is quite useful to introduce it at this point. As I say, Fraley introduces it a bit later on. So, let's just start thinking about what could happen. So we're going to have two groups. And I want to construct some sort of product of these two groups, which will itself be a group. So, well, the obvious thing to do first then is to say, well, forget about the group structure and just think about G and H as sets. And then I can construct the Cartesian product of G and H as sets. So this is the Cartesian product of the sets G and H. So I'm abusing my language left, right and centre. Here G and H were groups, and now suddenly G and H, we've forgotten about the binary operation, we're just thinking of them as sets. But that's the kind of abuse of language that we use all the time, and the context always makes it clear. If you want to be ultra precise, you can be, but then the notation just gets a bit heavy and the language gets a bit heavy. So just for a minute, forget that G and H are groups and just think of them as sets, the underlying set, and then I can construct the Cartesian product. And you would think, well, if I'm going to construct the product of two groups, perhaps I ought to start off with the product of the two underlying sets. So a typical element of the Cartesian product would be, say, G comma H, where little g is an element of big G and little h is an element of big H. So we're now going back to a picture that we had right at the beginning of the semester. But now these aren't just sets, they're groups. So a very special element, we've got to be a bit careful with notation now. We've got two identity elements. We've got the identity element of G, and I won't just call it E, I'll call it E sub G. And we've got the identity element of H, which I'll call E sub H. So the subscripts now are necessary because E, G and E, H might be different. I mean, they will certainly be different if G and H are different groups. So there's a special element here, which is the pair EG, EH. So we've got a special element in there, at least. So that's a good start, because a group ought to have a special element. So the idea is now, okay, we can take the product of these two sets and get the Cartesian product. It's even got a special element in there, because each of G and H has got a special element. The question is, can we make G cross H a group? In other words, do we have a binary operation on there that satisfies the group axioms curly G1, curly G2 and curly G3? So, can we equip the Cartesian product G cross H with a group structure? Because we know the Cartesian product of sets is quite a useful thing to have. It leads on to the idea of relations and functions and all the rest of it. And this would seem like a good idea because it means if we've got two groups that we know about, we can construct a new group using those two. So it'll give us more examples. And in fact, it turns out the direct product of groups is a very important concept in advanced group theory, which we're not going to get onto in this semester, but the direct product turns out to be a very important construction. So that's the question. Can we equip the Cartesian product G cross H with a group structure? So what do we have? So we've got a set G cross H. Okay, we've got a set, so that's a good start because all our mathematical constructions start with a set. But we need a binary operation. Well, we've got a binary operation on G, and we've got a binary operation on H, because we were given that G and H are groups. So the obvious thing to do is to try and use the binary operation on G and on H to construct a new one on G cross H. And really there's only one thing that you can do, and you've just got to check that it works. So we define this as follows. So let, say, G and H and G prime and H prime being G cross H. So I'm taking two elements of G cross H. So each element is an ordered pair. And notice now my prime here is just a way of distinguishing the second element from the first. It's nothing to do with inverses. I'm now not using primes for inverses, okay? So that's one element of G cross H, that's another one. So what I want to do is define GH, G prime, H prime. So I'm juxtaposing these two things. I want to multiply these two ordered pairs together. I'm not bothering putting a star or anything in between them. I'm just using juxtaposition now. So juxtaposition is being abused because juxtaposition is going to be used to mean three different binary operations. It's going to be used to mean the binary operation on G and on H and on G cross H. So I want to define the product of these two ordered pairs. So that's got to be another ordered pair because it's got to live in G cross H again. So I've got to occupy the first slot and I've got to occupy the second slot. Well, the first slot is stuff that lives in big G and the second slot is stuff that lives in big H. So what's the obvious thing to put in the first slot that's cooked up from ingredients on the left-hand side? I can only do stuff to do with G in this first slot, so the only ingredients I can use are G and G prime. And what's the obvious thing to do with G and G prime? Perhaps it's not that obvious the first time you see it. Well, G and G prime live in big G, so I can multiply them together in big G. So I can just do G, G prime. So that's using the binary operation in G. And I can do that because G has got a binary operation. So I can multiply G and G prime together in big G. That's another element of big G, and that's what goes in the first slot. And then once you've done that, the second slot is similar, but it's for H and H prime. So that juxtaposition is using the binary operation in H. So as I say, we really are abusing juxtaposition here. We're using it to mean three different products, three different binary operations. So it's once on the left-hand side and then twice on the right-hand side. So that certainly is an element of G cross H. Okay, that right-hand side certainly is an element of G cross H, because the first slot I buy something from big G, and the second slot is occupied by something from big H. So that is an element of the Cartesian product. So using the binary operations on G and H separately, we've constructed a binary operation on the set G cross H. So we've now got a set with a binary operation. So that's a good start. So okay, so it's a binary algebraic structure. It's a set with a binary operation. The question is it a nice binary structure? Do we have a group now? And we just have to check that everything works. So this is going to be an example of using the group axioms to check that we do actually have a group. Okay, so I think we should do this. So let's call it a theorem. So I'm just going to put everything together that we've done and state that we actually have a group. So the set G cross A, when you equip it with the binary operation that we've just defined, is a group. So that's what we're going to prove. So as I said, this is a good example. It's a kind of theoretical example, but it's a good example of using the group axioms. So G1. So G1, remember, is associativity. And this is not an exciting proof in a way, because everything just works as you want it to. So there are no surprises here, but I think we ought to go through it. So G1 is about associativity. To prove something about associativity, we need to take three elements, remember. So let GH, G prime H prime, and G double prime H double prime be in G cross H. So those are our three elements of G cross H. And I just want to prove associativity. So perhaps I'll go onto another sheet. So we have GH, G prime H prime. Now the brackets there are two kinds of brackets in this, what I'm writing down. There are the brackets which define the ordered pairs, and then there are the brackets that come from grouping, so I can do the binary operation. Okay? So these brackets mean I've got to multiply GH by G prime H prime first. So that means I get GG prime HH prime. So I've multiplied the first two together using the rule, the definition of the binary operation I had a few minutes ago. So remember, you keep the stuff in G together, you keep the stuff in H together. G and H aren't getting their hands on each other because there's no interaction between G and H. So that line follows by definition of the binary operation. So that's what you should have written here, by definition of the binary operation on G cross H. Now I've got two ordered pairs that I'm going to multiply together. So I do the first slot of the left one times the first slot of the right one. So I get G prime times G double prime, and I get H prime times H double prime. So that's using the definition of the binary operation again. So we're just doing it slot by slot, these binary operations. And now we just look at each slot separately. In the first slot, we've got something that looks a bit like half of the associativity axiom for G. So we're using associativity in G here, just to shift the brackets around. So I've used associativity in G there, and I can use associativity in G because G is a group, so the binary operation is associative. And similarly for the second slot, so that's using associativity in G and using associativity in H. And now we, as we've done once or twice in proofs like of this kind, of this flavour, we come in one way and then we just come out in kind of reverse. So that now we're in the middle, we're going to come out backwards. So this is GH times G prime G double prime H prime H double prime. So we're kind of coming out backwards now. That's using the definition of the binary operation in G cross H. And then we just do that again. So that's GH, and this is G prime H prime times G double prime H double prime. Again, using the definition of the binary operation in G cross H, just on this second bit. And that's it. So we've proved that the brackets here can be moved over here, and that's associativity. So as I say, it's not particularly exciting that, but we do use associativity in G and associativity in H, as you might kind of expect. So that was G1. What about G2, curly G2? So curly G2 is about an identity element. Well, I've already pointed out what the identity element probably ought to be. So let's consider E sub G, E sub G, E sub H in G cross H. So that's a special element of G cross H, because G has a special element, so I'm going to put that in the first slot. H has a special element, I'm going to put that in the second slot. So together I get a special element of G cross H. And so you think, well, if there's any justice in the world, which perhaps there isn't, this ought to be the identity element of G cross H. And in fact it is. So let GH be in G cross H. I want to prove that if I multiply this putative identity element by GH, I get GH back. So EG EH times GH. I want to show this is equal to GH. And you can see what's going to happen, I hope. I'll do this fairly quickly. We get EG times G and EH times H. That's by definition of the binary operation, which I'm not writing down, but I am saying. That's by definition of the binary operation. And as soon as we've got to here, we're just working in big G in the first slot and in big H in the second slot. So we've got the identity element of big G times an element of G, so that just gives the element back. And similarly we get H here. So that's using the identity element properties in G and H separately. Okay, so if I do this element on the left, it doesn't change the element on the right. And similarly, if we do it the other way around, we also get GH back. You can see how that's going to work. So putting it on the left doesn't change the element, putting it on the right doesn't change the element. So this indeed is an identity element, and we know that's unique, so that is what we need. Okay, so hence EGEH is, I'll put an identity element, but in fact we know it's the identity element because there's only one of them. An identity element for the binary operation on G cross H. So again, not too exciting. We're just doing stuff in G and we're doing stuff in H entirely separately from each other to get something on G cross H. Just a little aside here, nothing to do with this proof, but you can have more complicated situations where G kind of can get its hands on H a bit and twist things around, and then you get something called the semi-direct product, which is a bit more sophisticated. But we're not looking at that here. We're doing something very straightforward, which is why it's called the direct product. Okay, and then let's do G3, which says that we should have inverses. So let's take an element in G cross H. Well, if G cross H is going to be a group, G comma H better have an inverse. It's got to have a partner such that if you multiply the two things together, you get the identity element, which we've already established in G2. So, what candidate for the inverse, some element of G cross H, what candidate for the inverse might you suggest? It's got to be an ordered pair. What candidate would you suggest? Good. G inverse, H inverse. I mean, a little bit of thought suggests that there's nothing else we could write down, because we've got to have an element of big G in the first slot, and the obvious thing to do is to put little g inverse, and similarly for the second slot. Well, we've got to check it works. So if I do G inverse, H inverse, that element of G cross H times the element GH of G cross H, what do I get? Well, we've set it up so it works. First we use the binary operation, so we get G inverse G and H inverse H. Notice, by the way, more abuses of notation going on, because I'm using superscript -1 to denote the inverse in big G and also the inverse in big H, but the context makes it clear. Right, well now I've got G inverse next to G, so that's the identity element of big G, and we get the identity element of big H. So we've got this thing times the original element is the identity, so that does work at least on the left, and it also works on the right. As you will see, again just using the other half of the definition of inverses in G and in H. So we do have an inverse